ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ಈ ದಿನದ ವೆಬಿನಾರ್ ಡಾಕ್ಟರ್ ಕೇಶವ್ ಬುಲ್ಬುಳೆ ಅವರು ಎಲೆಕ್ಟ್ರೋಲೈಟ್ಸ್, ನಾನ್ ಎಲೆಕ್ಟ್ರೋಲೈಟ್ಸ್, ಎಲೆಕ್ಟ್ರೋಸಿಸ್ ಆ್ಯಂಡ್ ಇಂಡಸ್ಟ್ರಿಯಲ್ ಅಪ್ಲಿಕೇಶನ್ಸ್ ಆನ್ ಎಲೆಕ್ಟ್ರೋಸಿಸ್ ಎಂಬ ವಿಷಯದಡಿಗೆ ಅವರು ತಮ್ಮ ಜ್ಞಾನವನ್ನು ನಮ್ಮೊಂದಿಗೆ ಹಂಚಿಕೊಳ್ಳಲಿದ್ದಾರೆ. ಇವ್ರ ಬಗ್ಗೆ ಈಗಾಗಲೇ ನಾವು ಹಿಂದಿನ ವೆಬಿನಾರ್ನಲ್ಲಿ ಇವರ ವಿಚಾರವಾಗಿ ನಾವು ಮಾತನಾಡಿದ್ದೀವಿ ಮತ್ತು ಇವರ ಪರಿಚಯವನ್ನು ಮಾಡಿಕೊಟ್ಟೆ. ಆದರೂ ಮತ್ತೊಮ್ಮೆ ನಾನು ಇವರ ಪರಿಚಯವನ್ನು ಮಾಡಿಕೊಡಲು ನಿಮ್ಮ ಮುಂದೆ ಹಾಜರಿರುತ್ತೇನೆ. ಡಾಕ್ಟರ್ ಕೇಶವ್ ಎ ಬುಲ್ಬುಳೆ ಅವರು ಪ್ರಸ್ತುತ ಕೆಮಿಸ್ಟ್ರಿಯ ಪ್ರೊಫೆಸರ್ ಪ್ರಸ್ತುತ ನಿವೃತ್ತ ಕೆಮಿಸ್ಟ್ರಿ ಪ್ರೊಫೆಸರ್ ಆಗಿದ್ದರು. ಅವರು ಟೆಕ್ನಿಕಲ್ ಕನ್ಸಲ್ಟೆಂಟ್ ಪ್ರಾಜೆಕ್ಟ್ SP32, ಸಿ ಮೆಟ್ ಹೈದರಾಬಾದ್ ಮತ್ತು ಈ ಪರಿಸರ ಬೆಂಗಳೂರು ಇಲ್ಲಿಂದ ನಿವೃತ್ತಿಯನ್ನು ಪಡೆದಿರುತ್ತಾರೆ. ತಮ್ಮ ಸೇವಾವಧಿಯಲ್ಲಿ PhD ರಿಕವರಿ ಆಫ್ ಮೆಟಲ್ಸ್ ಫ್ರಮ್ ಎಂಡ್ ಆಫ್ ಲೈಫ್ ಪರ್ಸನಲ್ ಕಂಪ್ಯೂಟರ್ಸ್ ಈ ವಿಷಯದ ಮೇಲೆ PhD 2012ರಲ್ಲಿ ಮಾಡಿರ್ತಾರೆ. ಅದು ಅಲ್ಲದೆ KLE ಸಮೂಹ ಶಿಕ್ಷಣ ಸಂಸ್ಥೆಗಳಲ್ಲಿ ಹಲವಾರು ಹುದ್ದೆಗಳನ್ನು ಇವರು ಅಲಂಕರಿಸಿದ್ರು. ಅಷ್ಟೇ ಅಲ್ಲದೆ ಹವ್ಯಾಸವಾಗಿ ಮತ್ತು ಶೈಕ್ಷಣಿಕವಾಗಿ ಸುಮಾರು 10 ಡಾಕ್ಯುಮೆಂಟ್ರಿಗಳನ್ನು, ಅದು ಮೆಟಲ್ಗೆ ಸಂಬಂಧಪಟ್ಟಂತಾಗಿರ್ಬೋದು ಅಥವಾ ಕೆಮಿಸ್ಟ್ರಿಗೆ ಸಂಬಂಧಪಟ್ಟಂತಾಗಿರ್ಬೋದು, ಈ ರೀತಿಯ 10 ಡಾಕ್ಯುಮೆಂಟ್ರಿಗಳನ್ನು ಮಾಡಿ ಅವರು ಸಮಾಜಕ್ಕೆ ತಮ್ಮದೇ ಆದ ಗಣನೀಯ ಕೊಡುಗೆಯನ್ನು ನೀಡಿದ್ದಾರೆ. ಅದು ಅಲ್ಲದೆ ಕೆಲವೊಂದು ಈ ಡಾಕ್ಯುಮೆಂಟ್ರಿಗಳಿಗೆ ಪ್ರಶಸ್ತಿಗಳು ಬಂದಿವೆ. ಡಾಕ್ಯುಮೆಂಟ್ರೀಸ್ ಹ್ಯಾವ್ ರೀಚ್ ಸೆವರಲ್ ಥೌಸಂಡ್ಸ್ ಆಫ್ ಟೀಚರ್ಸ್ ಅಂಡ್ ಸ್ಟೂಡೆಂಟ್ಸ್ ಆಲ್ ಓವರ್ ದ ಸ್ಟೇಟ್ ಥ್ರೂ ಎಡುಸ್ಯಾಟ್ ಅನ್ನೋ ಅಪ್ಲಿಕೇಶನ್ ಮುಖಾಂತರ, ಕಂಪ್ಯೂಟರ್ ಅಪ್ಲಿಕೇಶನ್ ಮುಖಾಂತರ ಕರ್ನಾಟಕದ ವಿವಿಧ ಟೀಚರ್ಸ್ಗಳು, ಶಿಕ್ಷಕರು ಮತ್ತು ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಇದು ತಲುಪಿದೆ. ಅದು ಅಲ್ಲದೆ UGCಯಿಂದ ಹಲವಾರು ರಿಸರ್ಚ್ ಸಂಶೋಧನಾ ಪ್ರಾಜೆಕ್ಟ್ಗಳನ್ನು ಇವರು ಮಾಡಿದ್ದಾರೆ. ಸಂಶೋಧನಾ ಪ್ರಾಜೆಕ್ಟ್ಗಳನ್ನ ಇಂಡಸ್ಟ್ರಿ ಮೇಲೆ ಮಾಡಿದ್ದಾರೆ. ಕೇವಲ ಪುಸ್ತಕದಲ್ಲಿ ಮಾಡೋ ಥರ ಅಲ್ಲ, ನಾವು ಈಗಿನವರು ಮಾಡೋ ಥರ, ಆದರೆ ಇಂಡಸ್ಟ್ರಿಗೆ ಬೇಕಾದಂಥ ಹೆಲ್ಪ್ ಆಗೋ ರೀತಿಯಲ್ಲಿ ಸಂಶೋಧನಾ ಪ್ರಾಜೆಕ್ಟ್ಗಳನ್ನ ಇವರು ಮಾಡಿ ಮುಗಿಸಿದ್ದಾರೆ. ಅದು ಅಲ್ಲದೆ ಇವರ ಸೋಷಿಯಲ್ ವರ್ಕ್ ಆಗಿ he has trained several female prisoners of Bangalore Central Jail to make detergent powder, candles, chalk piece and floor cleaning ಈ ಥರ ವಸ್ತುಗಳನ್ನು ತಯಾರು ಮಾಡೋದ್ರಲ್ಲಿ ಬೆಂಗಳೂರು ಸೆಂಟ್ರಲ್ ಜೈಲಿನ ಅಭ್ಯರ್ಥಿಗಳಿಗೂ ಅವರು ಟ್ರೈನಿಂಗ್ ಅನ್ನು ನೀಡಿದ್ದಾರೆ. ಅದು ಅಲ್ಲದೆ ವಿವಿಧ ಹಂತಗಳಲ್ಲಿ 2005ರಿಂದ ಹಿಡಿದು 2012ರವರೆಗೆ 3 ವಿವಿಧ ಪ್ರಶಸ್ತಿಗಳು ಇವರಿಗೆ ಹುಡುಕೊಂಡು ಬಂದಿವೆ. ಅದರಲ್ಲಿ ಪ್ರಮುಖವಾದವು ಸಿಗ್ಮಾ 11 ಮತ್ತೆ ಸ್ಟೇಟ್ ಔಟ್ಸ್ಟ್ಯಾಂಡಿಂಗ್ ಟೀಚರ್ ಅನ್ನೋ ಅವಾರ್ಡನ್ನು 2011ರಲ್ಲಿ ಪಡೆದಿದ್ದಾರೆ. ಟಾಟಾ ಕೆಮಿಕಲ್ಸ್ ಬೆಸ್ಟ್ ಕೆಮಿಸ್ಟ್ರಿ ಟೀಚರ್ ಅವಾರ್ಡನ್ನು 2012ರಲ್ಲಿ ಟಾಟಾ ಕನ್ಸಲ್ಟೆನ್ಸಿಯಿಂದನೂ ಪಡೆದಿದ್ದಾರೆ. ಪ್ರಸ್ತುತ ಇವರು ಅಂದರೆ 2015ರಿಂದ ಇವರು ಟೆಕ್ನಿಕಲ್ ಕನ್ಸಲ್ಟೆಂಟ್ ಫಾರ್ ಮಿನಿಸ್ಟ್ರಿ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನಿಕ್ಸ್ ಆ್ಯಂಡ್ ಇನ್ಫಾರ್ಮೇಷನ್ ಟೆಕ್ನಾಲಜಿ, ಗೌರ್ಮೆಂಟ್ ಆಫ್ ಇಂಡಿಯಾ, ಭಾರತ ಸರ್ಕಾರದ ಎಲೆಕ್ಟ್ರಾನಿಕ್ಸ್ ಮತ್ತು ಇನ್ಫಾರ್ಮೇಷನ್ ಟೆಕ್ನಾಲಜಿ ಈ ವಿಭಾಗದಲ್ಲಿ ಸಲಹಾಗಾರರಾಗಿ ಕಾರ್ಯವನ್ನು ನೀಡ್ತಾ ಇದ್ದಾರೆ. ಇವರಿಗೆ ನಮ್ಮ ಕರ್ನಾಟಕ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಅಕಾಡೆಮಿಯ ಎಲ್ಲ ಪದಾಧಿಕಾರಿಗಳಂತ ಡಾಕ್ಟರ್ S. ಅಯ್ಯಪ್ಪನ್ ಚೇರ್ಮನ್ ಅವರು, CEO ಆದಂಥ AM ರಮೇಶ್ ಮತ್ತು ಹಿರಿಯ ವೈಜ್ಞಾನಿಕ ಅಧಿಕಾರಿಗಳಂತ ಡಾಕ್ಟರ್ ಆನಂದ್, ಡಾಕ್ಟರ್ ಶ್ರೀನಿವಾಸ್, ಡಾಕ್ಟರ್ ಉಮೇಶ್ ಗಾಡ್ಗೆ ಮತ್ತು ಆಡಳಿತಾಧಿಕಾರಿಯಾದಂಥ ಮಹಾದೇವಗೌಡ ಹಾಗೂ ಎಲ್ಲ ಸಿಬ್ಬಂದಿ ವರ್ಗದ ಪರವಾಗಿ ಮತ್ತು ಇಲ್ಲಿ ನೆರೆದಿರುವ ಅನೇಕ ವಿದ್ಯಾರ್ಥಿಗಳು, ಸಿಸ್ಕೋ, ವೆಬ್ಎಕ್ಸ್ ಮತ್ತು ಯೂಟ್ಯೂಬಲ್ಲಿ ನಡೆದಂಥ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿಗಳ ಪರವಾಗಿ ಹೃತ್ಪೂರ್ವಕ ಸ್ವಾಗತವನ್ನು ಬಯಸ್ತಾ ಇದ್ದೀನಿ. ನಿಮಗೆ ಸ್ವಾಗತ ಸರ್. ಮುಂದಿನ 40-45 ನಿಮಿಷಗಳ ಕಾಲ ತಮ್ಮ ಜ್ಞಾನವನ್ನು ನಮಗೆ ದಾರಿ ಎರೆಯಬೇಕಾಗಿ ಕೇಳಿಕೊಳ್ತಾ ಇದ್ದೀನಿ. ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್ ಸರ್.
ನಮಸ್ಕಾರ ಆಂಟೋನಿ ಅವರಿಗೆ. ಐ ಆಮ್ ಗ್ರೇಟ್ಫುಲ್ ಟು ಮಿಸ್ಟರ್ ಆಂಟೋನಿ and KSTA for having invited me to present a webinar on electrolytes, non-electrolytes, electrolysis and industrial applications of electrolysis. In fact, I joined KSTA in in welcoming all the participants for this webinar throughout the state and maybe throughout the country also. And I'm grateful to Anthony for having introduced me so nicely. I feel honored and I feel more responsible also. And as the topic indicates, electrolytes, non-electrolytes, electrolysis, and industrial applications of electrolysis, I always admire uh, this great man. I think I should get the next slide. Okay. I have designed my presentation in such a way that it is 60% knowledge and 40% skill. Means 60% theory and 40% experimentation, because I I appreciate the statement made by our great former president. Please focus on the third paragraph. When a principle learned in the classroom is borne out by practical experience, it creates a strange sense of excitement akin to unexpectedly running into an old friend among a crowd of strangers. Meaning is very simple. What all the theory you have learned, if it is going to be supplemented by the experiment, if it is going to be supplemented by the practicals, then what thrill you will have, what excitement will you will have is exactly similar to the one who is meeting his or her first standard or second standard friend after a gap of say 30-35 years. And this excitement you are going to see here in my presentation. And for today's presentation, what all I have listed is what are conductors and insulators, how the conductors are further classified as electronic and electrolytic conductors, differences between electronic conductors and electrolytic conductors, then further classification of only electrolytes, what are the factors that influence the degree of dissociation or degree of ionization of an electrolyte, then to experimentally support the term degree of dissociation, I have designed certain innovative experiments that you are going to see. Then most importantly, it is not enough if you study only theory for the sake of the examination. We should also know how these principles of electrolytes and electrolysis are used industrially in large scale to meet and to produce the products that we are using in day-to-day life, especially in the launching of satellite, in the making of paper, in the making of the textiles and so on. And for decoration and protection, we have been using a wonderful technology called electroplating. What is this electroplating? How iron is coated with zinc, copper, silver, and gold, that we are going to see step by step. And coming to the very first lesson of this title, electronic conductors and electrolytes and non-electrolytes. Any substance that conducts electricity in the solid state due to the mobility of valence electrons, due to the mobility of the electrons present in the outer subshell or outer shell on applying potential difference. These are all called conductors. And as you know, in the periodic table, 75% of the elements are metals. All the metals and their alloys are the best conductors. Those which conduct electricity right in their solid states are otherwise also popularly known as true conductors. Then what are insulators? Normally we call wood, plastic, etc. are insulators, because at any given higher or lower potential difference applied, these substances fail to conduct electricity due to the non-mobility of electrons. And such substances, right in their solid states, if they are unable to conduct electricity, they should be called insulators. Best example we see in day-to-day life: wood, glass, plastic, or in general any polymer fails to conduct electricity, and therefore these are classified as insulators. Then a new term in electrochemistry, normally second PhD students will be studying, and the part of today's topic is what are electrolytes. Electrolytes are also conductors. But the thing is, these electrolytes do not conduct electricity in their solid state, but conduct electricity either in their molten state, means substance should be heated to its melting point, that is called the molten mass, or substance can be dissolved in water or any other polar solvent, and in aqueous medium alone, if a substance conduct electricity, that should be called an electrolyte. Please note, these conductors conduct electricity only in the solid state, whereas electrolytes never conduct electricity in their solid state, but can conduct either in their molten state or in the aqueous solution form due to the mobility of ions. Earlier we saw due to the mobility of valence electrons, but here due to the mobility of ions, if any substance conducts electricity, that should be called an electrolyte. Then what is an ion? Charged atom is called an ion. Charged atom means it may be positive charge or negative charge. If any atom carries positive charge, that should be called a positive ion or cation. And if an atom carries a negative charge, that should be referred to as anion or the negatively charged ion. Then just like the insulator, we have got opposite of that, that should be referred to as non-electrolyte. A substance that does not conduct electricity either in the solid state or in the molten state or even in its aqueous solution form, after applying the potential difference, if it fails to conduct electricity, that should be called the non-electrolyte. All 100% covalent compounds or majority of organic compounds should be referred to as non-electrolytes. Then if we are able to classify the conductors as electronic conductors or true conductors and electrolytic conductors, they should differ in terms of their properties. What are the differences between electronic and electrolytic conductors? First one, as we have seen in the definition, they conduct electricity right in the solid state, whereas electrolytic conductors never conduct electricity in the solid state, but conduct electricity either in the molten state or in the form of solution in presence of a suitable solvent. That is very important. Then electronic conductors conduct electricity due to the mobility of electrons, or more particularly mobility of valence electrons, whereas these conduct electricity only due to the mobility of ions. And most importantly, the conductance of electronic conductors decreases as temperature increases, whereas this is opposite in case of electrolytic conductors. The conductance of electrolytic conductor increases as temperature increases, because as temperature increases, the increase in the degree of dissociation is found. Increase in the alpha value is found. What is the degree of dissociation? What is this alpha value? That we are going to see in the next explanation. But before this, very important is, in case of electronic conductors, there is no material flow at all. Very, very important. Only electrons move from higher potential to the lower potential. Whereas in case of electrolytic conductors, on passing DC current, material flows. Cations will move towards cathode, anions will move towards anode, and such a process of material flow of electrolytic conductors due to the passage of DC is all popularly known as electrolysis. And this makes very, very important step in the application in industries. Then how these further electrolytic conductors are classified. I am now focusing only on electrolytes. Electrolytes can be classified as strong electrolytes, then weak electrolytes. Further, they can also be referred to as non-electrolytes. Then what are strong electrolytes? The very differentiation is brought about in terms of this degree of dissociation value, generally in second PUC shown by the symbol alpha. What is this alpha? The ratio of number of molecules ionized to the number of molecules dissolved. Suppose I have dissolved 100 molecules of sodium chloride in water. If all 100 molecules dissolve and then split into 100 Na plus and 100 Cl minus, then the number of molecules dissolved is 100 and number of molecules ionized is 100. Ratio is equal to 1, and such a substance which has got alpha value 1, or not only sodium chloride, any salt that has got alpha value equal to 1, that they all should be called strong electrolytes. And generally we see 99% of inorganic acids, then hydroxides of first group elements, etc., all salts can be placed under this category called strong electrolyte. Then what is weak electrolyte? If any electrolyte has got degree of dissociation value less than 1, means number of molecules dissolved is 100, whereas number of molecules ionized is less than 100, and then ratio will be equal to, will never be equal to 1, it will be less than 1, and such a substance with alpha value less than 1 are all referred to as the weak electrolyte. Normally we say all organic acids, hydroxides of second group elements of the periodic table, etc., can be referred to as weak electrolyte. Then what is non-electrolyte? Suppose we have dissolved 100 molecules, and if none of the molecule has undergone ionization, then ratio is equal to 0. A substance that has got the alpha value 0 is popularly known as non-electrolyte. Generally, we say organic non-polar solids, organic non-polar liquids. These are all categorized under the non-electrolyte. Then we are focusing only on these two categories, strong electrolyte and weak electrolyte, and we hardly talk something about this non-electrolyte in the present discussion. Now, this already we have seen, let me not repeat. Now, there should be certain things which will decide the value of alpha. How the degree of dissociation of any particular substance is going to be affected by the factors. What are the factors that will affect the degree of dissociation value? In that, number 1, nature of electrolyte, whether the electrolyte is strong or weak. In the previous explanation, I mentioned any substance that has got the alpha value, degree of dissociation value 1, that should be called strong, and the one that has got the alpha value less than 1 is referred to as weak electrolyte. Then alpha value can also be terribly influenced by the nature of the solvent. Say for example, solvent is water. If I can put salt into water, it not only spontaneously dissolves but also ionizes. But the same salt, common salt, if I can put it in non-polar solvent like kerosene that I am showing here, the salt remains totally undissolved. No dissolution, no ionization, and hence, though salt by very nature is a strong electrolyte, just because we use a non-polar solvent, its alpha value is 0, and therefore it may act as the non-electrolyte. So this is very, very important. The nature of the solvent plays very important role in deciding the alpha value. Then temperature. Meaning of this temperature is a weak electrolyte can be converted into strong electrolyte provided the solution is heated from room temperature to higher temperature, right? That we are going to see step by step. And suppose to increase alpha value from less than 1 to 1, if you don't have heating arrangement, you can go on adding additional amount of solvent, dilute the solution so that dilution increases the alpha value. And Sometimes we will feel that presence of other materials can also influence the value of alpha. All these we are going to see with experiment designed and fabricated by me and my team. And you can see 4 bulbs are there, right? All these are 60 watt each, right? First bulb, second bulb are dipped into distilled water, 100% pure distilled water. Then the third one is dipped into solid salt, that is common salt. In the fourth container, I have got kerosene. Please remember this order, because in the next coming slides, you are going to see what is happening. Say, to the first container where I had placed distilled water, I am just squeezing a small amount of lemon. Lemon is rich in terms of citric acid. Citric acid is a weak acid. Weak acid is weak electrolyte. Weak electrolyte means it has alpha value less than 1. And when we talk about alpha value less than 1, number of ions produced in this container is quite less. We cannot peep into the solution, see whether number of ions produced is less or more. But this particular bulb glowing with a dim light indicates that it is a weak electrolyte. Same thing I shall repeat in the next slide, where I am putting little amount of glucose, right? Please recall, in the second container we had placed distilled water. I am now putting little amount of glucose that is normally put in saline water or dips, popularly known as dips. Fortunately, glucose dissolves in water. Dissolution does not mean that it undergoes ionization. Fortunately, water is polar solvent. Glucose is non-polar but soluble in water. Though the current is flowing in this bulb, it is not at all lit. There is no filament glowing at all. That means glucose, non-electrolyte, simply dissolves. There is no production of ions. Since there is no mobility of ions, there is no current conducted, and hence the bulb is off. Bulb is not at all glowing. The next experiment, quite interesting experiment, right? What I have done, to the same container, now I have put little amount of common salt, right? Common salt being a strong electrolyte, it spontaneously dissolves, ionizes, and number of ions produced is so abundant in nature that it is lit so brilliantly that the very conductance compared with the first and the second bulb, you can see it is burning with the dim light, because we had squeezed lemon and now it is brightly burning. Means strong electrolytes conduct electricity in a better manner than the weak electrolyte. Please note, the bulb dipped or the electrodes dipped into solid sodium chloride. The bulb is not at all glowing. What does it mean? The electrolyte, though the substance is capable of conducting electricity in this adjoining container, it fails to conduct here because in the solid state there are no free ions. No free ions means there is no mobility, and hence, due to the absence of mobility of ions, the bulb is not getting sufficient current, and hence it fails to light itself. And the last container, the electrodes dipped. The last container has got kerosene filled into already this container. Electrode dipped, and since this is a non-electrolyte, there is absolutely not a single ion at all. And though current is flowing, this bulb is also not at all being lit. And this is a wonderful experiment. One can do it, but only in presence of the experienced teachers or experienced supervisors, because we are passing AC current and not DC current. AC current does not bring about electrolysis. If I had used DC current, sodium chloride solution would have undergone electrolysis. And even teachers should not repeat this, right? Because whenever you are explaining, when you are engrossed in explaining, by mistake if you can dip your fingers into the solution wherever current is flowing, you may get a terrible shock, and therefore one has to be very, very cautious in demonstrating this experiment. One has to be doubly sure that you are standing on a wooden piece or some insulating material. You should have gloves, and the spoon or spatula that you are using should not be of metal. It should be of wood or plastic. This is a wonderful experiment to compare whether this substance is a weak electrolyte, strong electrolyte, then solid non-electrolyte, and 100% non-polar solvent is totally a non-electrolyte. And that's how these experiments are not shown in many schools and colleges because people are afraid of handling the AC current, and somehow one can do it with the DC current with a little amount of electrolysis. Tolerable electrolysis can also be experienced. And now we want what is called industrial applications of electrolysis. Normally I say theory guides, experiment decides. For the industrial applications of electrolysis, I have chosen this particular term, what is meant by electrolysis, then production of caustic soda or sodium hydroxide and its industrial applications. Most interestingly, electroplating. What is electroplating? What are Faraday's laws of electrolysis and electroplating industry, right? And for this, let us go to the next slide. What is electrolysis? The process by which electrical energy is used to produce a chemical change at the respective electrode. The very passage of electric current, if it can bring about the chemical changes at cathode and anode, that process should be called electrolysis. Now, whenever a substance is dissolved in a suitable solvent, say for example, sodium chloride, dissolved in water. Dissolution also brings about ionization. We get Na plus and Cl minus. Na plus ions will move towards cathode. Cl minus will move towards the anode. That's what we saw in the earlier distinction between electronic and electrolytic conductors, that in case of electrolytic conductor, there is material flow whenever DC current is passed. So metal ions migrate at cathode, cathode being the source of the electrons, the cations take up electrons and become neutral atoms. This entire process of electrolysis is beautifully governed by Faraday's laws of electrolysis, where second PhD students are generally studying all this. Now, this is an imitation of Nelson's cell. Nelson was the first man to produce hydrogen and chlorine and also caustic soda by the electrolysis of sodium chloride solution. How this is done industrially, that we are going to see step by step. But if any teacher wants to demonstrate this for the students, what you can do is you can do in the container where you have got here sodium chloride solution, right? I have purposely added a few drops of phenolphthalein indicator. Then two test tubes filled with water are kept inverted on two carbon electrodes nicely sealed. DC current is applied. After some time, you will find gas collected into both these test tubes kept inverted, and the one here you can see this is hydrogen gas, and at the other electrode we have got chlorine liberated, and slowly earlier colorless solution in presence of phenolphthalein indicator becomes pink. What all this means, you see there. Sodium ions, right? We have got net entire equation can be so represented: NaCl giving Na plus Cl minus. At the same time, water molecule also undergoes electrolysis to produce H plus and OH minus ions. You will find chlorine collected at anode, hydrogen collected at cathode and undischarged Na plus and undischarged OH minus ion left in the solution. These two combine to produce NaOH, popularly known in the market as caustic soda. In the lab, normally we call it sodium hydroxide. And in fact, hydrogen and chlorine so collected as the byproducts. If they are combining with each other, we get hydrogen chloride. That hydrogen chloride, when dissolved in water, you will get hydrochloric acid. You see, simple electrolysis of sodium chloride right at room temperature produces three important products, three industrially important products. One is hydrogen, another is chlorine, and the third one is sodium hydroxide. And normally, the sodium chloride solution we don't prepare, we get it from seawater only. And that seawater, rich in terms of sodium chloride, is popularly known as brine solution, right? So when brine solution is subjected for electrolysis, we get all these three industrially very important products. How the sodium hydroxide produced is used. Imagine, just look at this figure. Annual caustic soda production across India is around 3.1 million metric tons. Our country is the third largest producer of caustic soda in the world, because we use large amount of caustic soda in the production of soaps, both toilet soaps and washing soaps. We use it largely in the production of textiles, largely in the production of these detergents, in the production of pulp and paper, and thank God, it is all because of the nature of the electrolytes undergoing what is called electrolysis. This is what the Nelson cell. In the previous slide, I showed the imitation of Nelson cell. And such an industrially important product such as caustic soda, we would not have got if sodium chloride or brine solution did not have the unique property of undergoing what is called electrolysis. Now, everyone is using the mobile phone. Most of us are enjoying the television programs thanks to the satellites. How are these satellites placed in the orbit? That is by the use of rockets, right? And the life of the satellite is generally estimated, and whenever ISRO people launch the satellite, they will say this satellite is capable of serving the country for 5 years, 10 years, 15 years, like that. How do they calculate the age of the satellite? All that is because of one product used called unsymmetric dimethyl hydrazine. What is this unsymmetric dimethyl hydrazine? You see there, caustic soda produced using the electrolysis and using Nelson cell is made to undergo chlorine. Please note, chlorine is also produced in the Nelson cell by electrolysis. When both these combine, we get sodium hypochlorite. This sodium hypochlorite is made to react with ammonia, get chloramine. This chloramine is further made to react with ammonia produced by the well-known Haber's process. We get what is called NH2 bound to NH2, referred to as hydrazine. If I can replace one hydrogen by this end and another hydrogen from this end with one methyl group and another methyl group, that will be called symmetric dimethyl hydrazine. But what we do is, we take these two hydrogens out and we introduce one methyl group and another methyl group. Then the molecule becomes unsymmetric. Molecule becomes imbalanced. Such an unsymmetric dimethyl hydrazine is a wonderful fuel used to the last stage of the motor directly attached to the satellite. It provides fuel to the satellite not only to rotate about its own axis, but also to revolve around the Earth. And we should say hats off to Nelson, who introduced the process of production of sodium hydroxide and chlorine. And had there been no such sodium hydroxide, no such chlorine, we would not have got hydrogen, we would not have got unsymmetric dimethyl hydrogen, we would not have got this fuel, we would not have got the satellite, and we would not have enjoyed the mobile phone. So thanks to the property of electrolytes undergoing electrolysis, and therefore for all this raw material is salt obtained from sea. Therefore, there cannot be satellite without the brine solution. There cannot be satellite without the salt, and therefore I have named it as salt to satellite. For satellite, the basic raw material is salt only, ready to undergo electrolysis, ready to produce chlorine, hydrogen, and sodium hydroxide. So let us thank Nelson. Let us thank sodium hydroxide obtained by the electrolysis of sodium chloride. Now you see what is this plating. Coming to the last sector of my presentation, I said the very industrial application of electrolysis is in plating industry. We say, what is this plating? The process of depositing a thin layer of desired metal over another metal with the help of electric current. It's all referred to as electroplating. Generally, plating is carried out for both protection as well as decoration. Most of us have been seeing such GI sheets used for roofing purposes. GI sheets used for partition purposes. Basically, it is of iron. If iron sheets are used as they are, when such iron sheets are exposed to moist air, in the due course of time, rusting takes place. Rusting is not only poison to the metal beneath, but poison to the people who are handling it also. Therefore, such iron sheets will be coated with the zinc metal, and that is called galvanized iron. The process of coating iron sheets with the zinc is called galvanization, and this is generally in the market is referred to as GI sheet, GI wire used for the drying of wet clothes. And most of the time we get silver plate, silver articles in the market. 99% honest sellers will be selling only silver articles, but there will be 1% dishonest sellers also, where basically it is made out of copper, but over which a thick layer of nickel will be coated and a thin layer of silver also will be coated. All this coating is because of the electroplating, is because of material flow whenever DC current is passed through the electrolytic solution. This is quite interesting when I show you the next few coming slides, right? And all that credit of plating, extent of plating, how the thickness can be controlled and all that, that credit should go to this great man, Michael Faraday, who lived between 1791 to 1867. He is even today popularly known as greatest scientist of 19th century. In fact, he was the one who invented benzene, the mother of all organic compounds. He was the one who introduced the nomenclature called cathode, anode, anion, cation. And unfortunately, right, during his time, there were no Nobel Prizes given at all. I remember our Bharat Ratna, Professor C.N.R. Rao, many times uh, highlighting in his presentation that if Nobel Prizes were there during this period of Michael Faraday, Michael Faraday would have got at least 5 Nobel Prizes for his great contribution. In fact, he served as a bookbinder in a printing press. He used to sell papers on the streets, and such a person who was a bookbinder, who was an attender in the lab, went on to become the president of American Chemical Society, and later on Royal Chemical Society also. Hats off to this great man. Using Faraday's laws of electrolysis, how electroplating is done. Normally I say particularly in most of my presentation, Michael Faraday is a best devotee and ardent devotee of Lord Venkatesh. Why I have chosen this is, this huge gopura that you see, it is basically made out of copper. Over copper, gold is plated or gold is coated. How gold plating is done, that we are going to see step by step, right? You see, once with a great difficulty, having spent lot of time in the queue, once the devotees enter from here to here, will first salute this. This again is made up of, totally made up of copper, but coated with uh, gold, a thin layer of gold by electroplating. And I shall show you a tabletop model for electroplating. Suppose a material has to be plated with nickel, right? We will have nickel sulfate solution maintained at 60 degrees. To make it stable for a calculated length of time, we also add a buffer solution of phosphoric acid and its sodium salt. And suppose I want to plate this copper with nickel, right, which is silvery white in color. I will dip this material into nickel sulfate solution. A, a pure rod of nickel acts as the anode. Anything to be plated, anything to be coated, that should act as cathode. That should be remembered. We pass DC current, right? And as nickel ions from the solution move from the solution to the cathode, cathode being the source of the electron, every nickel ion takes 2 electrons to become nickel atom. This nickel atom gets coated over this material, and that reddish brown colored copper appears silvery white. This we are going to see in the next slide. You see, basically huge panel. These were actually plated in Bangalore. I am acknowledging the person who has helped me in getting this photograph. And these sheets were used for roofing in Lord Venkatesha temple in Tirumala, in TTD, right? We have got huge nickel bath. This nickel bath can hold thousands of liters of nickel sulfate solution, right? And this is acting as cathode for about 40 to 45 minutes continuously. Direct current is passed so that nickel ions from the solution go to the cathode. Cathode being the source of the electron, there they get discharged, they get neutralized, and nickel will be plated onto copper. You see how the person is dipping and how he will be looking at the voltage to be applied, and it is not less than 60 to 70 kilograms sheet, right? He is dipping it here. And please note, this is connected to the DC power supply and made to act as the cathode, right? And you see, once this is coated with or plated with nickel, it looks silvery white. This silvery white nickel coating is a must as a foundation coat or as a primary coat. Without nickel coating, directly we cannot go for gold plating. And over nickel coated sheet, this nickel plated sheet is further dipped into gold uh, solution. Gold solution is so prepared, you can see this is gold bath. This gold bath is prepared by dissolving potassium orocyanide or sodium orocyanide. At industry level, potassium salt are preferred to sodium salt because the potassium cyanide used to make this solution, though it is 80 times more poisonous, though it is 80 times more toxic in nature, plating made will be very, very durable. It will be as durable at least 10 to 15 years. There will not be any damage done to the gold plated done. And please note that for every liter of solution, we have to dissolve 6 grams of gold. The present rate of gold, even if you take say 60,000 rupees for 10 grams, it is going to be 6,000 rupees per gram, right? Such nickel plated, right? Original is copper, over which nickel plating is done. Thus, nickel plated material is dipped into gold solution, and here current is passed only for few seconds. If the current is passed for few minutes, right, there will be very, very thick coating of the gold. Thick plating of gold means we are drawing so much of gold, and the person who is the owner of the gold plating industry definitely will be put into terrible loss. And therefore, for nickel plating, normally 40 to 45 minutes current is passed, but here it is never more than 10 seconds. What happens at the cathode? Gold ions from the solution, right, migrate, go to the cathode being the source of the electron, right? We have got 3 electrons gained, and at the end, gold atoms produced are deposited onto the nickel coating. That's how we have got gold plating done. This is another view of gold plating, right? And now most of the idols, most of the vigrahas will be not only protected but also decorated with gold plating. Here, a small idol of Lord Krishna to be coated with nickel, and finally to be coated with gold also. Anything to be plated should act as cathode. Here, Lord Krishna is acting, Lord Krishna's vigraha is acting as cathode, and initially it is nickel plated by dipping that into nickel sulfate solution, and in the end the same nickel plated is dipped into gold uh, solution, that is potassium orocyanide solution. Over that, a thin layer in terms of say 0.25 micron or 0.5 micron gold will be coated. That is how the original copper vigraha becomes gold plated vigraha. Then we have got, these are all the padukes of Lord Venkatesha. These were plated in our Pinya industry, surface chem finishers industry. These are originally of copper, made of copper. Over copper, nickel coating is done, and over nickel plating, gold is plated. Anybody who has visited TTD for Lord's Darshan must have seen this grill work. All this grill work is also plated with the gold. Basically, these are copper, but the same procedure, right? Electrolysis taking place, nickel plating, and ultimately gold plating. Recently, we got this Lord Panduranga, who is a manifestation of Vishnu and Krishna, made of copper, right? Ultimately, we wanted to plate it with gold, a thin, very, very thin layer that's called flash, right? It's simply dipped and taken out of the gold solution. And this technique is once again due to electroplating. This technique is once again due to electrolysis of the electrolytes, right? Step by step, as shown here, right? Industry is going to be huge. Industry is also huge investment industry, and you see step by step, these are all the wonderful applications of electrolytes, wonderful application of electrolysis process, and that's what normally we say. Michael Faraday invented the laws in showed the entire world that electrolytes can undergo electrolysis, and therefore generally I said whoever visits TTD will chant Venkatramana go in the long live Faraday's laws of electrolysis. Instead of go in the, I prefer devotees should chant this long live Faraday's laws of electrolysis. So let us thank properties of electrolytes and the process of electrolysis. Let us also thank this greatest scientist of 19th century, Michael Faraday for inventing laws of electrolysis. So with this, I thank all the participants for having viewed, for having appreciated these industrial applications of electrolytes and electrolysis. I also profusely thank KSTA for having invited me to present this webinar on electrolytes, non-electrolytes, and industrial applications of electrolysis. Thank you all.
Thank you, sir. Sir, thank you, sir. This is
Thank you, sir. Thank you.
ಸೊ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ತಾವು ಕೊಟ್ಟಂತ ಎಲೆಕ್ಟ್ರೋಲೈಟ್ಸ್ ಮೇಲೆ ಕೊಟ್ಟಂತ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮ ಮಕ್ಕಳಿಗೆ ಬಹುತರವಾದ ಇನ್ಫಾರ್ಮೇಶನ್ ಗಳನ್ನ ಕೊಟ್ಟಿರ್ತಕ್ಕಂಥ ಸಂದರ್ಭದಲ್ಲಿ ಸೊ ಎಲೆಕ್ಟ್ರೋಲೈಟ್ಸ್ ಎಂದರೇನು, ಎಲೆಕ್ಟ್ರೋಲೈಟ್ಸ್ ಇರ್ತಕ್ಕಂಥ ವಿಧಗಳು ಯಾವುದು ಮತ್ತು ಎಲೆಕ್ಟ್ರೋಲೈಟ್ಸ್ ನ ಯಾವ ಭಾಗಗಳಲ್ಲಿ ಯಾವ ರೀತಿ ಉಪಯೋಗಿಸ್ತಾರೆ ಅದನ್ನ ಎನ್ನುವುದನ್ನ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಕನ್ನಡ ಮತ್ತು ಇಂಗ್ಲಿಷ್ ಎರಡರಲ್ಲೂ ಕೂಡ ಬಹಳ ಸ್ಫುಟವಾಗಿ ನಮಗೆ ಸಿಕ್ಕಿದಂತ 1 ಗಂಟೆಯ ಅವಧಿಯಲ್ಲಿ ಅದ್ಭುತವಾಗಿ ತಿಳಿಸಿಕೊಟ್ಟಿರೋದಕ್ಕೆ ಸೊ ಇಟ್ಸ್ ಅನ್ ಇಮೆನ್ಸ್ ಪ್ಲೆಜರ್ ಟು ಥ್ಯಾಂಕ್ ಯು ಸರ್.
Thank you, sir. Thank you very much.
For this wonderful speech on electrolytes. This talk has given many information to the students. So I gratefully once again thank you, sir, and towards KSTA and personally, sir.
Thank you very much, sir. Thank you.
And I also thank our KSTA CEO, Dr. Ramesh, sir, for this encouragement to organize this talent search program. I am gratefully thank you, sir. And I also thanks our chairman, Ayappan, sir, and our colleagues, staffs, and technicians, and WebEx team, and all the attendees, our students. Once again, thank you, sir.
Thank you, sir. Thank you very much.
ಸೊ ವಿದ್ಯಾರ್ಥಿಗಳಲ್ಲಿ ಒಂದು ಮನವಿ, ಇವತ್ತು ನಮ್ಮ ಬುಲ್ಬುಲೆ ಸರ್ ಕೊಟ್ಟಿರ್ತಕ್ಕಂಥ 2 ಪ್ರಶ್ನೆಗಳಿಗೆ ಸೋಮವಾರ ಬೆಳಿಗ್ಗೆ ಉತ್ತಮವಾದ ಉತ್ತರಗಳನ್ನು ಇವತ್ತು ಯಾರು ಅಟೆಂಡ್ ಆಗಿದ್ರೆ ಎಲ್ಲಾ ವಿದ್ಯಾರ್ಥಿಗಳು ಕೂಡ ಬರೆದು ಕಳಿಸಬೇಕೆಂದು ನಮ್ಮ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಇಲಾಖೆ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ಮತ್ತೊಮ್ಮೆ ಸೂಚಿಸುತ್ತಿದ್ದು, ಹಾಗೂ ಸೋಮವಾರ ನಡೆಯುವ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಪ್ರತಿಮಾ ಕಣ್ಣೇಲ್ವಾಲ್ ರವರು ಸ್ಟ್ರೆಸ್ ಮ್ಯಾನೇಜ್ಮೆಂಟ್ ಸ್ಕಿಲ್ಸ್ ಫಾರ್ ಸ್ಟೂಡೆಂಟ್ಸ್ ಎನ್ನುವ ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ಕೊಡಲಿದ್ದಾರೆ. ಸೊ ಇದೇ ರೀತಿ ವಿದ್ಯಾರ್ಥಿಗಳು ಅಂದು ಕೂಡ ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ಹಾಜರಾಗಬೇಕಾಗಿ ತಿಳಿಸುತ್ತಿದ್ದೇವೆ. ಹಾಗೂ ಬೈಜೂಸ್ ವತಿಯಿಂದ ಪ್ರತಿದಿನ ಕಡ್ಡಾಯವಾಗಿ ಹಾಜರಾಗುವ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಉಚಿತವಾಗಿ ತರಬೇತಿ ನೀಡಲು ಕ್ರಮ ಕೈಗೊಂಡಿರುವುದರಿಂದ ಎಲ್ಲಾ ವಿದ್ಯಾರ್ಥಿಗಳು ಮುಂದಿನ ತರಗತಿಗಳಲ್ಲಿ ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ಹಾಜರಾಗಬೇಕೆಂದು ಮತ್ತೊಮ್ಮೆ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ಸೂಚಿಸುತ್ತಿದ್ದೇವೆ. ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ.
Thank you very much.